Today we're going to talk about linear search with some intro to complexity of algorithms. Now these short video lectures are not supposed to replace the class lectures. They capture some important aspects of the class lecture. So in class we will discuss more examples and go into more details. But if you have any comments about these video lectures, you can post them into YouTube. We'll continue to improve these video lectures while keeping them to 10 to 15 minutes. The big ideas in this lecture are talking about specification functions and talking about data structure invariance and talking about loop invariance and then analyzing the linear search and talking about big O notation. Now the search is a very common problem. The search problem is that given a data set, we want to find an element as fast as we can. So one of the ways we can start talking about search is with specification functions. Now what I mean by specification functions is functions that I know are mathematically true. So for example, I can start with an array segment from I to j where the bracket, close bracket, left bracket I means that I is included and the open bracket j means that j is not included. So we are essentially looking at the array segment from I to j minus 1. And so the find function, the specification, the correct specification for a find function would be that if I is greater than or equal to j, then we are looking at an array of size 0, then it must be false. X cannot be in this segment. And if ai is not equal to x, and then we look at the next segment starting from I plus 1. So if we can't find it here, then we would shorten the segment and look in the next segment. And if ai is equal to x, then we will return true since we found it. So one of the first things that I'm going to do is to translate this recursive definition into a specification function which I know to be true. And I will use the specification function to write specs when I write the linear search. I also will try to write specification for a sorted list, because one of the things we're going to do is to look at the sorted list. If you're given a sorted list, can we do the search faster? So if you have a list of size n greater than or equal to 0, which is given from 0 to n, then we say A is sorted as long as A of k is less than or equal to A of k plus 1 for all. This should be k from 0 to n minus 2. Now, so this sorted function can be written as follows. You write a loop and you say that as long if you find something that's not in that order, we're going to return false, and it's not sorted, otherwise you return true. So now one of the things we want to talk about is writing contracts. So let's start with linear search with contracts. So first of all, we want to write some contracts for this is-in function. So the first contract I'm going to write is a precondition. I will require that the n to be greater than or equal to 0 and the n to be less than or equal to the length of the array I'm looking at. What this means is that I may be looking at from 0 to some segment of the array, not necessarily the entire array. But that's one of the specifications I need. And then I need to have another contract here, and which can be a loop invariant. A familiar loop invariant to us now is that I is greater than or equal to 0 and I is less than or equal to n. Now we have done the proof of this many times, so I'm not going to prove this is a loop invariant. So that's a linear search with contracts. Now suching in a sorted array, if you have a sorted array, we can do the search faster. So for instance, here's a piece of code that will search a sorted array. So lin search looking for x in the array from 0 to n minus 1. So the conditions are n is greater than or equal to 0 and n is smaller than the length. We also require that a to be sorted. So this is a specification function that we know to be true that we can use in our linear search algorithm. We also know that if the result is -1, that means if you don't find the element if the element or the x is not in the list, then we must return -1. If you return something between 0 and n-1, we know that we must know that the result must be equal to f result must be equal to x. So here's a piece of code that makes it work. Now notice that I have added this condition here to exit the loop early in case ai becomes greater than x. So if ai becomes greater than x at some point, that means x is to the, if you look at this to be the I, then if x exists, it must be to the left. But if you don't have it, if you don't find it here, then you're not going to find it, so you can exit. So we can write the familiar loop invariant, and inside the loop, if it happens to be, it's possible that you can get into the loop when ai equals to x, then you will return the index of that element. Now there's a bug here. The bug here is, if you carefully think about it, when you exit the loop, because this is a loop invariant, we do know that I is greater than or equal to n. The loop invariant tells us I is less than or equal to n, and therefore these two implies that I can be equal to n at the end of the loop. But the problem is, this condition is checked again, therefore we are checking as of n to be less than or equal to x. Now that will cause a problem because this index is out of bounds. So we have a problem here. So how do we fix it? Well, we can easily fix it by switching the two conditions. So that's as easy as that. How does it work? This is called the short circuit evaluation. So short circuit evaluation means that if you have a Boolean condition, if you have a Boolean condition, the conjunction, we have if I happens to be in, if this is false, because if I is equal to n, that would be false, then you don't even check the second condition. Therefore we never run into the trying to access an array index bound element. So therefore having that I less than n will save us from having this sort of an error. Now we can strengthen the loop invariant to prove the post. So how do we strengthen the loop invariant to prove the post condition? Now what we're going to do is to add, we have the standard loop invariant which will help us with some terminal value of I if we exit the loop normally. Otherwise there are possible loop invariances here. Either I is equal to 0 or ai minus 1 is strictly less than x. Now how do we prove this? Now if I is equal to 0, that's as you enter the loop. Now if you go through the loop and if you did not return, that means ai was ai minus 1. We did not, just before we incremented, ai minus 1 is not equal to x, and ai minus 1 was not greater than x, otherwise we would have returned, so it's less than or equal to x. So this implies that ai minus 1 is strictly less than x. So we prove that loop invariant is true there. So this loop invariant satisfies that I is equal to 0 or ai minus 1 is less than x. Now how do we prove that the loop invariant implies the post condition? So our post condition is, if you return the result -1, then it could not be in the array. But if you return the result between 0 and n, which would be this case, then we would know that a of result has to be x. So let's take the case that it returned -1 as a result of normally terminating the loop. If that's the case, we do know that one of the loop invariances is I is less than or equal to n, and the loop exit condition is I is greater than or equal to n, and therefore this implies I is equal to n. So if it returns I is n, because of the loop invariant ai minus 1 is less than x, implies that as of n minus 1 is strictly less than x. So x is way beyond the last element, so x must be somewhere here, and therefore we could not find it. Now let's assume that we return -1 as a result of having this condition. Now since we know that on the line, if you look at the ai minus 1 and if you look at a of I, now this loop invariant condition says that ai minus 1 is less than x, so x must be here. But this condition says that ai was greater than x, so that means x is less than x, so it says that x must be here. But that means x is somewhere between the two things, and it could not be in the list. And therefore we prove that this first condition is true. And so the cost of search is really measured by counting operations. So for example, you can count the operation, how many comparisons, how many checks that we do. We do have one check here, perhaps two, and maybe three. So we can write a function of the cost as a function of n. So if you have n operations, then it would be 3 times n. That would be the cost of n. So one of the big thing that we're going to try to do is to describing the runtime as a function of n. So if I define f of n to be 3 times n, and if I double the size of the data set, this would become 6 times n. So in other words, the function is linear in this case, so it's proportional to the, so for instance a linear function would look like this, f of n equals n. So we do know that if you increment the size of the data set by 2, the runtime would also increase by a twofold. And if you develop a notation to describe this, we talk about this notion called the asymptotic complexity of algorithms. What we say is that f of n is big O of g of n, that if you can bound after some n naught the f of n function, like for instance we know that n is going to be big O of n squared, because n is always less than n squared. Okay, but we can have other sort of functions there. Now this one shows the sort of some standard graphs, the exponential function and quadratic function, let's call it n squared here, and then maybe the linear function, maybe the logarithm function, some of the standard functions. And we'll talk about these things in more detail in the next lecture.